Okay, let's see. Where were we? We were talking about vector space, and we had a set of vectors, and we had the notion of what it means for them to be linearly independent. And recall what that meant was that if we had a linear combination of them, C1 V1 through CR VR being equal to the zero vector, the only way that that can happen is if all of the constants are zero. That's what it means for them to be linearly independent. And recall the picture is if we have two vectors like this, then they're linearly independent, but if we had too many vectors, three of them in this case, the answer would be no, these are not linearly independent. Okay, so let's go on now to a very important definition. So please wake up, everybody, pay attention. The situation is we're given a vector space V and a bunch of vectors V1 through Vn. We say that set of vectors is a basis of the vector space if the following two conditions hold. So first of all, the vectors V1 through Vn are required to span the vector space. Second of all, they're required to be linearly independent. So let's reiterate that. We have a basis. The fact that they span the vector space says that there are enough of the vectors. And to say that they're linearly independent says that there aren't too many. So it's two conditions of sort of an opposite nature, and put them together it means you have exactly the right number of vectors. And here's an example. If V is R2, then one possibility is to take the vector 1, 0 and the vector 0, 1, which look like this. They're clearly linearly independent, and they span, because if you have any vector xy, you can write it as x times the first vector plus y times the second. And again, they're linearly independent because if you had some linear combination of them, well, how can that be equal to 0? Only if x and y are both 0. Well, here's another possibility. Instead of taking that basis, take this basis. Take any two linearly independent vectors in R2. Those are a basis of R2 because I told you they're linearly independent and they automatically span R2. Well, let's look at another example. Let's take R3 and let's take W to be the following subspace. The subspace of vectors such that x plus y plus z is equal to 0. This is a subspace. What's the basis of it? Well, here are two vectors in it, 1 minus 1 0 and 0 1 minus 1. And I claim that these are a basis of this subspace. Why is that? Well, let's see. They're certainly linearly independent. They don't point in the same direction. And do they span? So we have to check. Can I write any vector in the subspace as a linear combination of V1 and V2? Well, let's take such a vector. I need to write it as something times this vector plus something else times this vector. And if you look at the first coordinate, since there's a 1 here and a 0 over here, the only way you can get an x in the first coordinate is by having an x here, and similarly, looking at the last coordinate, I must have a minus z here. So my only hope is if I can write this vector as x times this minus z times 0, 1, minus 1. So the question is this really true? Well, the only problem is the middle coordinate. So on the right-hand side, I have minus x minus z for the middle coordinate. On the left-hand side, I have y for the middle coordinate. And is it true that y is equal to minus x minus z? Well, yes, because the sum of the three coordinates is 0. So you're in good shape. So this w has a basis consisting of two vectors. Okay, here's another very important definition. I think you're already awake from last time, so I won't remind you to wake up again. Here we go. V is a vector space. The dimension of a vector space is the following. You simply take the number of vectors in a basis of it. Okay, so what does that mean? It's obviously supposed to coincide with the intuitive notion of dimension that we've been talking about all along, and that is to say Rn. What's the dimension of Rn? Well, take the following basis. You take V1 and V2 and so on to be the vectors with a 1 in one place and 0 everywhere else. There are obviously n of these vectors. They're linearly independent and they span. And so that says that the dimension of Rn is n. And of course, that's the whole point of the definition of dimension. That's supposed to make that work. Okay, well, let's check something here. The dimension of a vector space is the number of vectors in a basis. So, well, there can be more than one basis, so the following must be true. If you have any two bases of a vector space, they must have the same number of vectors, or else the dimension wouldn't be a meaningful concept. And this is true. So let's take a look at the proof of this. This is a useful thing to look at. Suppose I had two bases of a vector space, v1 through vm and w1 through wn, and let's suppose that one was bigger than the other. Well, the fact that the v's are a basis says that you can write w1 as a linear combination of the v's, which we'll write like this. And similarly, w2 through wm. So you conclude that this list of vectors, w1 through wn, can be written as the vectors v1 through vm times a matrix on the right, which is m by n. And the ith column of this matrix is expressing the ith vector wi as a linear combination of the vj's. Okay, so we have this equation here, and what's the rank of this matrix A? Well, remember that's the number of pivots, which of course is less than the number of rows, less than or equal to the number of rows. And since n is bigger than that, it must be that the columns of A are not linearly independent, since n is bigger than m. And what that means is that, well, a linear combination of the columns is given by multiplying a vector on the right, which is to say this linear combination involving c1 through cn is a linear relation on the columns. And so we have this fact that the v's times a times this vector with the c's is 0. And in other words, we've just obtained a relation that the w's times the c's is equal to 0, which is a linear combination of the w's is equal to 0. But that's a contradiction. We assumed that the w's were a basis. So it can't be that n is bigger than m, so these two bases actually have the same number of vectors. Okay, let's conclude with one last topic here, which is the four fundamental subspaces of a matrix. We have an m by n matrix, and we think of that as a map from Rn to Rm. And the null space is, remember, a subspace of Rn, and the image is a subspace of Rm. And the transpose matrix is, of course, an n by m matrix, which we can think of as a map going from Rm to Rn, which is to say, I'll draw it here in the same picture, it's going in the other direction. So we have these two subspaces, the null space of A and the image of A, and now applying this to the transpose, we have two more subspaces, the null space of A transpose and the image of A transpose, and these lie in the opposite spaces, and here are our four fundamental subspaces associated to a matrix A. Two of them in Rn, and two of them are in Rm. Now one last thing about this is, so we're working with this m by n matrix. So remember, the image of a matrix is the same thing as its column space. And that's a subspace of the target space, Rm. And look at the image of A transpose. Well, that's the column space of A transpose. And that's a subspace of Rn. And, well, the column space of A transpose is the same thing as the row space of A. So we have the following picture. We have this map from Rn to Rm. And just looking at the images, the image of A is over here. It's the column space of A. And the image of A transpose is over here, and that's the row space of A, which is the same thing as the column space of A transpose, and by symmetry we can put the row space of A transpose here. So in terms of row and column spaces, this is the picture. Okay, that's a good place to stop. We'll see you next time.